This is the second lecture dealing with differential equations and their solutions. Here we look at the second order equations and we consider the complex roots. From the previous lecture, we found the second order differential equation to look like equation 1, a0 y double dot plus a1 y dot plus a2 y equals 0, or in operator form, a0 d squared plus a1 d plus a2 all times y t is equal to 0. We then made the following substitutions. We substituted y equals e to the bt, y dot, so dy dt, b equals e to the bt, y double dot, so the second derivative of y with respect to t was b squared e to the power bt, and we noted that b was equal to minus a1 over a0. So given equation 1, imaginary roots occur when a1 squared minus 4a0 a2 is less than 0, and this is derived from the quadratic formula. Then x1 is equal to alpha plus beta I, and x2 is alpha minus beta I. The general solution, and here we're continuing the numbers from the last lecture, is given by equation 5. Yt equals k1 e to the alpha plus beta I all times t plus k2 e to the alpha minus beta it. And recall that the alpha minus beta I and the alpha plus beta I are derived from the characteristic equation. Equation 5 can then be rewritten as yt is equal to e to the alpha t all times k1 e to the beta it plus k2 e to the minus beta it. And recall that e to the plus or minus ix is simply equal to cos x plus or minus I times sine x. So this is the real component and this is the imaginary component. As a result, we can write equation 6 as yt is equal to e to the alpha t all in times k1 plus k2 multiplied by cos beta t plus k1 minus k2 multiplied by I sine beta t, which therefore gives us equation 7, yt equals a alpha t all multiplied by a1 cos beta t plus a2 sine beta t. The time path of y will involve cycles because of the cos and the sine here. Again, we define an angle delta for which tangent of delta is equal to minus a2 over a1, such that a1 is equal to a3 cos delta and minus a2 equals a3 sine delta. All right, so in other words, what we have is that minus a2 here is simply sine delta divided by a1 cos delta, and we put an a3 up and below. If we do that, so we come up with this a3, we define this a3, then 7 can be rewritten as y equals e to the alpha t all multiplied by a3 cos beta t plus delta. So a3 determines the amplitude, 2 pi over beta is the period, delta governs the phase, and e to the alpha t magnifies if alpha is greater than 0, or dampens if alpha is less than 0, the amplitude. So let's look at an example. So we take y double dot, so d squared y divided by dt squared, that's what y double dot is, minus 6y dot, so minus 6 times dy dt, plus 13y equals 0. And we assume that at time period t equals 0, y is 2, and the first derivative of y is minus 2. So in operator form, we have d squared minus 6d plus 13, all multiplied by yt equals 0. The characteristic or auxiliary equation is given by x squared minus 6x plus 13. If we solve it using the quadratic formula, we end up getting 3 plus or minus 2i. Using equation 7 then, we get yt equals 3t a1 cos 2t plus a2 sine 2t. So then we use the initial conditions to find the values of a1 and a2. At t0, y0 equals 2, y dot 0 equals minus 2. So then the cos of 2t equals 1, sine of 2t equals 0, and e to the 3t equals 1. So then what we get is a1 equals 2, 3a1 plus 2a2 is minus 2, and from that we get that a1 is 2 and a2 is minus 4. So then the final solution is given here as, so this would be the solution to equation y, number 9. Y as a function of t is equal to e to the power 3t plus 2 cos 2t minus 4 sine 2t. Alternatively, we can look at the tan of delta. Remember, the tan of delta was equal to that, what was it, the sine over the cosine. And what we get is minus delta, tan delta is minus a2 over a1 equals 2, and 2 equals a3 cos delta, and 4 equals a3 sine delta when you solve that. And therefore delta, if you take the tangent of minus a2 over a1, so the tangent of 2, then you get 1.107 radians, and a3 is 4.47. Based on the equation 8, so this equation up here, then what we find is the solution yt equals 3 e to the 3t 4.47 times cos 2t plus 1.107, which is then the answer or the solution to this initial problem here, y double dot minus 6y dot plus 13y equals 0. Now we have to look at the non-homogeneous case in the case of a second order differential equation. So in that case, we write it as this: a0 d squared y over dt squared plus a1 dy dt plus a2y is equal to k. K is not equal to 0, which means we have a non-homogeneous solution. We can write this out in this form here, or in operator form like this. Solution procedure is as was the case for difference equations. We find the solution to the homogeneous equation where we set k equals 0, and we denote that y to the power h, or yh, pardon me, just for homogeneous. And then we find a particular solution, yn, that satisfies the non-homogeneous equation. The general solution is then y equals yh plus yn. For yn, the most straightforward solution is y equals c, as was the case with difference equations. Since dy dn, this yn equals c, is equal with respect to t, when you take the derivative with respect to t, equals 0, and the second derivative with respect to t squared is 0, then a2c equals k, so c equals k over a2. a2 cannot be 0. For an nth order equation, c is equal to k over an, and an cannot equal 0. As with difference equations, if y equals ct fails, we try y equals ct squared. A particular solution will always be found by the time y equals c to the power tn, where n refers to the order of the differential equation. So let's look at an example. That's the best way to look at this. Y double dot minus 6y dot plus 8y plus 9. Here's your non-homogeneity. It'd be minus 9 if we brought it to the right-hand side. At t equals 0, we have that y equals 3, y dot equals 2. Those are our initial conditions. For the homogeneous solution, the auxiliary equation is x squared minus 6x plus 8 equals 0. So we get x equal 4 and x2 equals 2. So then we put that into y equals k1 e to the 4t plus k2 e to the 2t. For the non-homogeneous component, we try y equals c. Here we get 8c equals minus 9, or c equals minus 9 over 8. So the non-homogeneous component solution is minus 9 over 8. So then the general solution is given by y equals k1 e to the 4t, where that 4 is your x1, plus k2 e to the 2t, where that 2 comes in here, minus 9/8. So what we have to do is find out what k1 and k2 are. So at t equals 0, k1 plus k2 minus 9/8 equals 3, and 4k1 plus 2k2 equals 2. Remember that for the first derivative, at time t equals 0, this holds, and we put a 0 here, and we get these terms go to 1. So we get k1 plus k2 minus 9/8 is 3, where 3 is our initial condition. If you go back here, here's 3 is your initial condition, and y dot equals 2. Now we have to take the derivative of this function with respect to t, and that becomes k1 multiplied by 4 e to the 4t plus 2 times k2 e to the 2t, which gives us this 2k2. When t equals 0, you get a 1, and t equals 0 is a 1 here. We get 4k1 plus 2k2 equals 2. Solving those two, we get k1 equals minus 25 over 8. K2 is 29 over 4. Then a complete general solution is given by y equals minus 25 over 8 times e to the 4t plus 29 over 4e to the 2t minus this 9/8. Complications arise if we do not have distinct roots to the auxiliary equation, but we have seen how these can be resolved when we have multiple roots. In other words, try y equals ct rather than y equals c, or complex roots, where we often get a solution whereby yt oscillates over time. So if we then go to nth order differential equations, we find that the second order differential equation case with quadratic auxiliary equation illustrates adequately the varieties of behavior that are possible in the time path of the dependent variable as t grows. These depend in turn on whether the solution to the auxiliary equation consists of distinct costs, distinct roots, multiple roots, or complex conjugate roots, the imaginary component. So the nth order differential equation has a higher degree auxiliary equation. Solutions will possibly consist of a combination of distinct, multiple, and pairs of complex conjugate roots. The general solution is y equals k1 e to the x1t plus kn e to the xnt, where the x's are the solution to the auxiliary equation, and then k1 and up to kn, so your k's are determined but from the initial conditions. So the ki values are determined from initial conditions. One then needs n minus 1 initial conditions for t equals 0. Special computational techniques are required and available for solving certain classes of higher order equations, but these are beyond our concern. Higher order differential equations can be expressed as systems of first order linear differential equations. Next, we look at how we might analyze these systems of first order linear differential equations using phase diagrams, but note that we do not consider partial differential equations in this course. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.